Hey Level 2s, and welcome back to Lesson 9 of 2.4 Atomic Structure and Bonding. And today we're going to be learning about exothermic and endothermic reactions in terms of both energy change and bonds breaking and bonds making. And we're going to describe why exothermic reactions are more common. So this part normally we would do quite a bit of practical work, and so we still will, but I'm just going to wait until we get back together, because to do heat practicals, you really want to feel the heat changes and see it for yourself. So videos are a bit lame for that. Okay, so what is an exothermic reaction and what's an endothermic reaction? When you've been in science previously, and one of the most common experiments is when you add some magnesium to some hydrochloric acid. And a lot of you will always say, oh miss, it's getting hot, it's getting hot. And that is a really great qualitative observation where you feel that it's getting hot. And you could measure that temperature change using a thermometer. You know, you could quantify it by doing initial temperature and then final temperature, and you would see that it got hotter. And so that must mean that when that reaction happens, heat is being released, right? Because the temperature is going up. And so that type of reaction, when heat is released, is called an exothermic reaction. So now it's got a name. So when we feel the temperature get hotter during a reaction, that's an exothermic reaction. And then the opposite, if you see something where the temperature goes down, that's an endothermic reaction. And that's what we're going to learn about today. And we talk about it as being the system and the surroundings. And it's just that the reaction itself is classed as the system and the surroundings is kind of everything else. And so because we feel the test tube get hotter, the surroundings are getting hotter. And then when we do endothermic, the reaction itself is absorbing the heat energy, and therefore the surroundings are giving that energy, and that's how come the temperature is going down. So those are two new terms for today. So exothermic and endothermic, and that's what we're talking about the whole time. So let's keep going. So just to make sure we're all in the same boat here, is that this is all about energy changes, okay? So when energy is released, it's exo. When energy is absorbed, it's endo. And this happens during some chemical reactions. And when heat energy increases, we know kinetic energy of the particles increases. So if energy is being released, the particles move around more than when they're colder, they move around less. Okay. So we need to kind of build a picture with this topic continuously. So you'll just have to bear with me as we go through a few things. Now, you heard me talk about just before system and surroundings. So these pictures are quite good for various things. So system is kind of the reaction itself, and environmental surroundings is everything outside of that reaction. Okay, that's the easiest way to talk about it. There are two other situations that we need to think about when we talk about this sort of topic, and that's an open system and a closed system. And these are really easy. An open system is where something can escape. So generally it's got no lid, and it'll be a gas that escapes. So you could imagine if you've got a beaker in a reaction between calcium carbonate and HCl, which you would have seen many a times before. During this reaction, you produce calcium chloride and CO2 and H2O. Now, CO2 is a gas, and if there's no lid, then that gas will escape, and we say that reaction is an open system, okay? And a closed system is one where either there's a lid, sometimes a lid is just sufficient, or a closed system is where there's nothing can escape, essentially, okay? So only energy can exchange with the surroundings, not energy and matter. And when we say matter, we mean a substance. So these are just terms, and it makes more sense as we keep going. So what is enthalpy of a system? H. And that's a big part of today's lesson. So every substance has a certain amount of energy contained in them, and that energy is stored in the chemical bonds or in the intermolecular forces. And how that energy is stored is actually potential energy, okay? It's you can kind of think of it as like we eat food because food has got potential energy stored in it. Well, any substance has got potential energy stored in it too. And when chemicals react, the difference between the enthalpy of those reactants and the enthalpy of the products is what causes that heat change that we observe. So if you look down at the graph, we've got reactants down here and we've got products down here, and it's the difference between these two values which is the enthalpy change. And if you look at this diagram down the bottom here, you can see that the products have got more energy than the reactants. And if the products have got more energy than the reactants, then in this process, energy must have been absorbed. And if energy was being absorbed, we know that that type of reaction causes the surroundings to get colder, and that means this type of reaction is endothermic. So as I say, as we go on with this topic, we just build and build and build a picture of these exothermic and endothermic reactions. Now that energy change that occurs during a reaction is called the enthalpy change, and we often measure the enthalpy change using a temperature change. And the symbol for enthalpy of a reaction, so the R stands for the word reaction, triangle means the change, and H stands for enthalpy. And so that's what we're going to be talking about the whole time. So what's the enthalpy difference between the reactants and the products? So we've already said all this, but just make sure that we're all on the same boat. So when heat is added to a system from the surroundings, okay, there's an increase in enthalpy, and that just means all we're saying here is that the reaction is absorbing heat energy, and therefore it's endothermic, okay? And if it's absorbing heat energy, the products have got more heat energy than the reactant. So we say that enthalpy change is positive. And when heat energy is released from the system to the surroundings, there's a decrease in enthalpy. So the products have less enthalpy, and that's because energy is being released. And if energy is being released, the products must have less enthalpy, and therefore this is a negative enthalpy reaction. So just making sure we've got it for a third time, and I'm now linking in a graph to make sure here. So endothermic reactions is where energy is absorbed by the system, okay, and so the surroundings get colder, and so we see a decrease in temperature. And so what that means is that if the system is absorbing heat energy, the products must have a higher amount of energy than the reactants. And if the products have a higher amount of energy than the reactants, then we say the enthalpy change has been positive because there's been a gain, okay? Whereas though exothermic reactions, they release heat energy to the surroundings. So this means that the surrounding particles get hotter, and that means that the actual system has lost energy. And so that means that the reactants have a higher energy than the products, and so it's been a negative enthalpy change. This is a practical we'll do when we come back together, so don't stress about this. Okay, so exothermic reactions. Now I'm going to give even more details as we go through this topic. So we've already said exothermic reactions release heat energy to the surroundings, okay, and so therefore if they release heat energy to the surroundings get hotter, so therefore you'd see an increase in temperature. So an example of that was that magnesium and hydrochloric acid. The test tube got hotter, which means energy was being released, and therefore we know that it's exothermic, which has got a negative enthalpy. Okay, so we've got that. So now I'm going to show you a graph. Now I know that the bottom axis has been cut off annoyingly, but it's an arrow down the bottom here. Okay, and that's basically course of the reaction or time. And up here, this is actually potential energy. It often just says energy, but it's potential energy. So you've got reactants here and you've got products here, and we understand that because we've worked out that energy is being released to the surroundings. So I think most of us are fine with that. And therefore, because energy is being released, your products have got less energy than your reactants. So hopefully we're all okay there. So the difference between the two, so this part here is your negative enthalpy of reaction, okay? So that's how much energy is being given out to the surroundings. Now we can actually add a heck of a lot more information when we talk about heat energy reactions, and I'll spend a lot more time talking about the exothermic because I can explain it, and then it's the opposite for endo. So the reaction I'm about to write for you guys right now is the combustion of methane. So when we combust something, it means to burn an oxygen. And if it completely combusts, you produce carbon dioxide and you produce water. And you guys will see that I'm doing these Lewis structures right now. Well, actually, I'm drawing the shapes. I'm missing the Lewis structure step, but that's because we know how to do it. And you guys can actually see that this is what methane looks like, and this is what O2 looks like, and this is what CO2 looks like, and this is what water looks like, okay? And there's a reason for that, because I'm going to talk in a second about how we actually look at these reactions as a whole. I'm just going to add right now a second oxygen so it's fully balanced. Okay, so why have I drawn this reaction? So this reaction here, team, when something reacts, what you've got to realize is that there is actually both an endothermic aspect to it and an exothermic aspect to it. And it's whichever one is bigger that makes the overall reaction endo or exo. And so let me make this more clear. When we go to react methane with oxygen, in order for them to react, all of the bonds within these particles must first break. Okay, that makes sense. These bonds have to break in order for the atoms to rearrange and form the products. Okay, so how do they just break? Do they just willy-nilly just break? And the answer is no. Like, I mean, energy has to be put in order for these molecules to break apart. And so if we look here, in order for this reaction to take place, you've got to break, I'll just do break here. We've got to break 4 CH bonds, and then you've got to break 2 O double bond O. So 4 of these and 2 of these. So that's what has to break. And then we've got to make bonds. We've then got to make 2 CO double bonds and 4 HO bonds. So hopefully that makes sense. So we've got to break these bonds in order to make these bonds. Now, in this example, this reaction is actually exothermic, which releases heat energy. So what that actually means is we can actually put a bit more detail now. Now, in order to break bonds, you have, as I said before, it wouldn't willy-nilly happen. You've actually got to put some energy in so that they can break. And so if you're putting energy in, energy is being absorbed, and that means that breaking the bonds in the reactants is actually an endothermic process, okay? So that's actually endothermic. It's absorbing heat energy. And you may not know this, so this could be the first time you're hearing it, but this is really cool. When you actually make bonds, so the bond making in the products, this is actually an exothermic process. So when in the past you've sat by like a fire on the beach or something like that, and you've toasted your marshmallows and you've thought, this is so lush, I'm sitting here and it's all getting nice and hot, you've probably thought that the reason why it's hot is because the wood is burning. And actually it's not. The wood burning, you're actually breaking the bonds. So that part of the process is actually endothermic. So breaking the bonds in the wood is endothermic, absorbing heat energy. And the reason why we feel warmth by sitting by the fire is because carbon dioxide and water is being made, and it's the making of those bonds that releases heat energy, and that's the heat we feel, which is pretty cool. So the whole time we've probably thought about sitting by that fire incorrectly. So the next time you see wood burning with someone, you can be like, did you know it's not actually the wood burning that causes us to feel heat? It's actually the making of the carbon dioxide and water bonds that releases the heat that we feel, which I reckon is pretty cool. So carrying on. So when we talk about an exothermic reaction, we've got to consider that in the reaction there's also an endothermic aspect. But because the whole thing is exothermic, what really we're saying is more energy was released when making the bonds in the products than was taken in to break the bonds in the reactants. So we're comparing them, okay? So more energy is given out by the bonds forming in the products than is taken in to break the bonds in the reactants. And so you can see that here, we can visually see that on this graph, that this hump here is known as the activation energy. The activation energy. Now the activation energy, we're going to do a whole section on this in the topic 2.6, but for now, activation energy really simply is the energy needed to start a reaction. And in order to start this reaction, we have to break the bonds in our reactants, and that's this amount here, this blue arrow, okay? And then when bonds are made, they release heat energy, which is this red arrow. And you can see here the red arrow, the making of bonds, is far bigger than the blue arrow, which is the energy to break the bonds, which is why this reaction is overall exothermic, because more energy is released when making the bonds than is taken in to break them. And that is exothermic. So exothermic can be described in this energy way. So more energy given out by making bonds in the products and taken in to break in reactants, and bond making is exothermic. Now I'm going to come back in a second to do the endothermic. See you soon.